All right, well, today I'm going to go over a little lab I like to do to help us understand what a radian measure is of an angle. And, you know, in math and science, we have different units of measure for distance. For example, we can have miles versus kilometers, and they're just different units. And they're standard units that we would use to measure things, like inches are different than centimeters. Well, angles can be measured in degrees, which most of us are very, very used to, or they can be measured in radians. And I like to do this Smarty activity because it helps us understand the difference between what one radian is and 1 degree. Okay, so what we need to do this little lab is a pencil, obviously, a straight edge, and some Smarties, which is the best part of this lab. Okay, so without further ado, what we need to do is we need to open up our Smarties, which is the best part because I love to hear the paper crinkle. There we go. The papers are crinkling. All right, so there are our Smarties. Okay, now the instructions on this lab say, using the smaller circle, do the following. Use Smarties to measure the radius. Okay, so you might say, well, what is the smaller circle? The smaller circle is on this next page. I have 3 concentric circles here. Concentric meaning they have all the same center. And I want to measure the radius with Smarties. Instead of in inches, we're going to use Smarties. Okay, so here we go. So I'm going to measure the distance, or how long the radius is, in Smarty units. And can everybody see that my radius of the small circle is 3 Smarties? So I'm going to write in here 3 Smarties. Okay, then it says remove the Smarties from the radius and lay the same number of Smarties along the curve starting where the small circle intercepts the positive x-axis. Keep in mind your Smarties should curve along the arc of the circle. So what we're going to do now is take our Smarties and we're going to move them along the arc, the outside arc. Okay, so there we go. There's my arc, my Smarty arc. And then the instructions say, use a ruler to draw a line segment from the origin to the end of the Smarties arc. So this is my Smarties arc, and here's my straight edge. Pull my straight edge out. From the origin to the edge of my Smarties arc. So I'm going to put a little mark here. All right, and then I'm going to move my Smarties out of the way so I don't get any lead on my Smarties. Okay, so there we go. We're going to draw. This is going to be the terminal side of our angle here, if I can get it lined up. Here it is. There's my angle. Now in standard position, I should use my straight edge for that too, huh? Let's just be consistent here. Right, so that would be my central angle. All right, so there we did it, and we're going to call this central angle. So it says now, examine the central angle formed by the line you just drew with the positive x-axis. This central angle is an angle of rotation that intercepts an arc whose length is equal to the blank of the small circle. Well, what did we do to create this central angle? Well, we measured the radius in Smarties, and we made an arc of equal length, didn't we? Okay, so this is going to be equal to the length of the radius. So this is the radius. Can I spell radius? Probably not today. Of the small circle. Okay, and so it says remove the Smarties and repeat the process for the medium and the large circle. So here we go, we're going to do the same thing. So I'm going to measure the radius of the medium circle. I'm going to use colorful ones. Well, that looks like it's going to be about 5 Smarties. I'm going to put 5 here. And let's measure the large one. Looks like it's only going to require 2 more. So it looks like the large circle has a radius of 7. And now I'm going to do my Smarty Arc measurement, right? So I'm going to put my Smarties along the curved arc here. And then I'm going to put a little mark where they end here. Okay. And then I'm going to move them and use my straight edge. Well, look at that. Lo and behold. Certainly looks like it's the same angle. Same central angle. I wonder if the same's going to hold true. If you're a betting person, I bet you know what the answer is. If I use my 7 for the outer circle, here's my arc, my Smarty Arc. Now, using Smarties as a measurement tool is pretty crude, but we're being reasonably consistent, aren't we? It helps if I'm actually on the circle there. Okay, now when I say by crude measurement, I mean these aren't they're probably pretty uniform in design. You know, they're circle shape here, but okay. So I think you get the point. Does it matter what the size of the circle is? And the answer is no. I still continue to get the same. And now you can almost eat the Smarties, but not yet. But you notice, no matter what the size of the circle, if I create a Smarty Arc the same size as the radius, same length as the radius, what am I doing? I'm creating a central angle of the same size. So this would be my central angle of rotation. This would be theta. So it doesn't matter whether I have 3 Smarty length arcs or a 5 Smarty length arc or a 7 Smarty length arc. I can still get the same angle. So let's see what the lab says. Are the central angles on all 3 circles similar? And of course we would say yes. So I'm going to put a yes here, sure. In fact, not only are they similar, they're the same. The central angle you drew is called 1 radian. That means that's the measure of 1 radian. If someone was absent from class today or hadn't watched this video, and they wanted to know how to draw an angle whose measure was exactly 1 radian, what would you say to them? What would you tell them to do? Oh yeah, I heard somebody in the back say, well, Mrs. Muller, I would tell them to measure the length of any radius, measure the length of a circle, no matter what its size, measure the radius, and then create an arc of equal length, and then draw an angle that intercepts that arc, and then I'd have a central angle that was 1 radian. So this angle measure here, this theta, is equal to 1 radian. Okay, and measure. So now let's think about that. 1 radian almost looks like it could be close to, if this is 90, if this angle of rotation is 90, this certainly looks like it could be maybe 60 if we were approximating. And we're going to figure out what it is exactly later in this video. But if this is a measure of 1 radian, think about that. How does that compare? If this is 90 degrees and this is 1 radian, what does 1 degree look like? 1 degree is probably so small we can barely see it. different from the positive x-axis if we drew it in standard position. Do you see how 1 degree would be really, really small? Because I got to get 90 of them in here. 90 degrees to get in there to go to 90 degrees. Now, 1 radians is very big compared to that. Okay, so if I wanted to have you now, after having done this exercise, you know, what I want you to do is on this circle here, without using your Smarties or measuring, mark off a central angle whose measure corresponds to 2 radians. Okay, so we saw what 1 radian looked like. So pause the tape or pause the video and you draw something that looks like it's 2 radians. And then I'm going to draw mine. And then when you are done, you can see what mine looks like. Okay, you're back. All right, well, now this is obviously a rough sketch, but this is what 2 radians looks like approximately. Okay, because remember, 1 radian looks like about this, right? And then I just drew it double the size. Okay, so that's what 2 radians looks like. If I wanted to draw one that was 4 radians, what would I do? I would just say it's double this size, and it would probably end up over here somewhere. The terminal side would end up over here. And then 5 would be 1 more. And then all the way around almost looks like it's 6, but we'll see. We're going to do a calculation here and figure that out. Okay, now what we're going to do is figure out how many Smarties it takes to do the quarter of the large circle. So we're going to take our Smarties and put it on the outside here and see how many of them it takes to measure. Remember that a Smarty arc is 7, right? We said it was 7. So how much is a quarter circle? Quarter would fill up to the 90-degree mark, wouldn't it? Sorry, I'm a little bit awkward with my Smarties here. So let's see how many that would be. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it takes 11, okay? 11, so we'll put 11 here. It takes 11 Smarties to do a quarter circle. Okay, so if 11 takes a quarter circle, how many Smarties is it going to take to do half of the circle? Yeah, I heard it, 22. Good. What about 3/4 of the circle? 33. And the whole circle is going to require 44 Smarties. And sadly, my package does not have 22, 33, or 44. We need more Smarties to do the entire circle. Okay, so now you can eat your Smarties while we're doing this because we figured that out. Okay. But what I wanted to do is suggest to you that 7 Smarties here makes a Smarty arc. Right, this right here is a Smarty arc. So 7 Smarties makes a Smarty arc. Okay, because that's 1 radian. Okay, so I want to know how many Smarty arcs it takes to make a quarter circle. Well, it's going to be 1 Smarty arc and then some. So how do we figure that out? Well, what we do is we say we want 11. We want 11 over 7. Because, you know, if it takes 7 to do 1, I'm going to have 11 sevenths to be a quarter circle, all right? What about for half a circle? Well, that would be 22 over 7. And then 3/4 of a circle would be 33 over 7. And then whole circle would be 44 over 7. And now this is where the fun begins. Well, the fun's actually eating the Smarties. I get that, but now we're going to pull out the calculator and see what numbers we got here. Actually, I'm going to do it this way. Okay. So I'm going to take, and let's clear this out. I'm going to take 11 divided by 7 and see what fraction that is, what decimal that is. Well, we find that that decimal is, let me get comfortable writing here, 1.571428.571. Now I'm putting a lot of digits just so that we can, see what they are. All right. What about 22 over 7? Let's do that. 22 divided by 7. Well, that's going to be just 2 times this number, which is 3.142857143. And then 33 divided by 7 is going to be 3 times, which is 4.714285714. And then 44 divided by 7 is going to be 6.285714.286. Okay. Now, I'm hoping that one of these numbers is screaming at you, one that we might have seen before somewhere in math. I'll give you a second. What are you thinking? What are you thinking? What are you thinking? Well, it's this one, isn't it? This 3.14. We've seen that before. Well, guess what? That's approximately, whoops, my approximately is a little weird. It's approximately pi. That's right. And if this is pi, what do you think 6.28 is approximately? Yep, you'd be right. That's about 2 pi. And then 1.57 is going to be half of this number, so this will be approximately pi over 2. And then this one will be about 3 pi over 2. Now, if you don't believe me, let's do some calculations here. Let's do second pi and press enter. And we get 3.141592654, which, is pretty, when we're measuring with Smarties, to get 3.14 instead of 3.1415, that's pretty amazing. Because let's think about how crude our measuring item is. It's pretty amazing to get that half of the circle will be 3.14 Smarty Arcs, which is pi. And a Smarty Arc, remember, a Smarty Arc is 1 radian. So this is 3.14 radians. And then if we go 2 times that, second answer, we get 6.283185. You see how that's really close to 2 pi. So that's 2 pi radians. So what does all that mean? Let's go back to our Smarty Arc picture here. If this is 1 radian, right, this measures 1 radian, we can say, if this is 0 radians, like we started out with 0, and halfway around we said was, all right, because the halfway around was pi radians, so I can put pi here. And twice, if I go all the way around, it's going to be 2 pi. Well, what is halfway between 0 and pi? So meaning, if I were going to go halfway, what would that angle be in radians? Well, if 180 degrees is equal to pi, the 90 degrees is going to be equal to pi over 2, because it's halfway between 0 and pi. Now, what about down here? Well, I'm between pi and 2 pi, or 180 and 360. And so this is going to be 3 pi over 2. And then we end up at 2 pi. So now we've broken these quadrants up into radians. So that's pretty cool. So now I know that my quadrants are my quadrantals are in increments of pi. Okay? Now, the question here is, how do you think the numbers in the last column would differ if we use the same activity on the medium circle? Well, Okay, so let's try it with the medium circle. Okay, so I'm going to do that with a different color with a medium circle. Which would require me to do the Smarties on the medium circle. So let's do the Smarties on the medium circle. Let's just have some fun here. So I need the quarter circle. So we have 5 that are this Smarty Arc here. One of the Smarty Arcs is 5. And then I think it's 3 more, right? I would add 3 more, maybe? Looks like I'd add 3 more. So I'd have 8. Okay, so a quarter circle would be 8 if I'm using the medium. This I'm going to use M for medium. Okay, then it would be 16, and then it would be another 8, right? So that would be 24, and then another 8 would be 32, right? And then my fractions would be, remembering it takes 5, my Smarty Arc is 5, so it would be 8 over 5, 16 over 5, 24 over 5, and then 32 over 5. Now let's just see what the fractions do, just to be investigatory. Clear this out. We're going to go 8 divided by 5. Well, we get 1.6, which is a rounded version of this. It's not as accurate, is it? What about 16 divided by 5? 3.2. Still not as accurate, but close. 24 divided by 5. 4.8, the rounded version of this. Pretty close. Using Smarties. 32 divided by 5. 6.4. Still, these are not as accurate using the medium circle as they are the big one. So why do you think that is? Well, I think the bigger our circle, the more accurate we're going to be in the number of Smarties, because we take some of the inaccuracies of the space being small, right? Because we might have a better, this could be 5 point something or 8 point something, the size of the circle. Like if I even did a bigger circle, I think we'd get more accurate, is what I'm trying to say. Not very gracefully, but that's what I think. All right, so let's do a little bit of a summary here. Okay, I'm going to do a really quick XY plane here. Okay, and we're going to label it again. First, we're going to use radians. So this will be, I'm going to do red for radians, if that's all right. So it's going to be 0, I said, pi. And then this is going to be pi over 2. And this would be 3 pi over 2. And if I were to go all the way around, it would be 2 pi. Okay, now let's try degrees. Degrees would be 0 degrees, and then up here would be 90 degrees, and here would be 180, and then here would be 270, and then all the way around would be 360 degrees. Okay? Now, what if I know that pi is about 3.14, right? And we said pi over 2 was about 1.57, and 3 pi over 2 was about 4.71, and 2 pi was about 6.28. So it's kind of nice to know what those decimals are, because not all angles and radians have pi's in them, right? Because 1 radian is right about here. Okay? So it's nice to know what these decimals are. So if I wanted to know what quadrant an angle that measured 2 radians would be in, the terminal side, if it was positive, would be in quadrant 2, because it's greater than 1.5 but less than 3.14 radians. Okay? All right, so we're going to do something called name that quadrant. Now, what does that mean? That means I'm going to give you an angle, and we're going to figure out what quadrant the angle is in. We're going to draw it and then figure out what the positive coterminal is, negative coterminal, and name the quadrant. Okay, so let's say I want I'm going to give you an angle. Theta equals 2 pi over 3. Okay, so let's graph that real quick. First of all, it's a positive angle, so its rotation is going to go counterclockwise. And I like to label this as 0 and then pi, and then pi is equivalent to 3 pi over 3, isn't it? Because that's the same as saying 1 pi. Now this says 2 pi over 3. So it's like I'm breaking pi up into thirds. So it would be 1/3 pi and then 2/3 pi. So it's going to be a quadrant 2 angle. There it is, quadrant 2 angle. That would be theta. Okay, so let's do a positive coterminal and a negative coterminal and an expression for all. Okay, so positive coterminal, well, what do I have to do to go all the way around to hit it again? I heard it. Yep, I have to add 2 pi to that. But what is 2 pi in thirds? Well, that's 6 pi over 3. So I'm going to take 2 pi over 3 and add 6 pi over 3 and get 8 pi over 3. Because all the way around is 6 pi over 3. Okay, good. If I wanted a negative coterminal, that's going to start here on the positive axis and rotate clockwise. Well, I'm going to go a full 3 pi over 3. And then I'm going to go 1 more pi over 3, which makes us a negative 4 pi over 3. That would be the negative coterminal. And then for all of them, I'm going to take my original angle, which is 2 pi over 3, and then I'm going to add a multiple of 2 pi, right? And so we're going to say 2 pi times n, where I define n as an integer. Okay, so we named the quadrant. This is quadrant 2. And then I did my coterminal. All right, let's do another one. Let's stick with thirds. 10 pi over 3. Here we go. Let's draw our xy plane. All right, here's my initial side. 10 pi over 3, knowing that this is 3 pi over 3. And this is 0 or 6 pi over 3. And I want to go 10. Okay, so I'm going to go all the way around at least because I got to do 6 pi over 3. There we go, 6 pi over 3. And then I want to go 4 more. Well, that means I have to go to at least here and then 1/3 more. And that would be 10 pi over 3. All right, so let's list a positive coterminal, a negative coterminal, and an expression for all. Okay, so a positive one would just be if I went from this positive initial side counterclockwise to here. So it would be, I'd go full 3 pi over 3 and 1 more. So this would be 4 pi over 3. And then a negative one would just be if I went part of the way to 3 pi over 3. So this would be 1/3, 2/3. So this would be negative 2 pi over 3. And an expression for all of them would be, I take my original angle, 10 pi over 3, plus 2 pi n, where n is an element of the integer set. All right, we're going to go dark. We're going to go negative. And this is obviously a quadrant 3 angle. Okay. All right, next one. Theta equals negative 4 pi. Okay, so I'm going to label as I always do, 0, pi, and then this is 2 pi. Negative 4 pi means I'm rotating clockwise, so I'm going to go all the way around at least once. That's 2 pi, and I got to go another full 2 pi. So here we go, and then that would be 4 pi. That's a quadrantal. The quadrantal. And so it doesn't have a quadrant because it's a quadrantal. And then we're going to do a positive coterminal and a negative coterminal and an expression for all coterminals. Okay, so a positive coterminal would be if I were just to go from the positive x-axis and rotate counterclockwise, and that would just be 2 pi. And then a negative one would be if I went one time around, so negative 2 pi. And an expression for all coterminals would be, I'm going to take my original angle here, which is negative 4 pi, plus 2 pi, n, and an element of the integer set. So we'll just do n multiple times around. Okay, let's do another one. Theta equals 7 pi over 2. Okay, let's see here. Let's draw our angle. Here we go. Here's my xy plane and standard position. This is 0, pi, and then this is 2 pi. Now this is a half, right? So I'm going to label my half. So this would be pi over 2. This would be 2 pi over 2. And then this is going to be 4 pi over 2. And this, of course, is 3 pi over 2. So I need to go 7. So all the way around is 4. So here we go. I'm going 4. And now how many more do I have to go? Well, what do I have to add to 4 to get to 7? Well, I have to add 3. So I'm going to go 3 pi over 2. So I have to end up here. And that's another quadrantal. Of course, I had to do 2 in a row. All right, so a positive coterminal. Well, that's just going to be 3 pi over 2, it looks like. Now remember, there are infinitely many answers because we can add 2 pi as many times as we want to get coterminals. So I'm just giving you the ones that I see right away. A negative coterminal means I'm going to start on the positive axis and rotate clockwise, which would be negative pi over 2. And then an expression for all of them would be 7 pi over 2 plus 2 pi n and an element of the integer set. All right, now I chose angles, right, that had pi's in them, but not all radian measures have pi's in them. So let's do 2 more, and I'm going to do theta equals 4.2. Now I know that that's radians because I don't have a degree mark. Okay, so here we go. And it's positive, so I'm rotating counterclockwise. And I'm going to label this 0, pi, 2 pi like I always do. And then this is pi over 2 and then 3 pi over 2. And then I want you to remember again what the decimals are here, right? Because we said that this is 3.14, 6.28, and about half of this is about 1.57. And this is 4.71. But I only need to go 4.2. Now this is just going to be an approximation. So it's going to have to be in quadrant 3, my terminal side. So I'm going to just, put it right here. And again, this is an approximation, but this is a quadrant 3 angle. And it's 4.2 because we've gone beyond 3.14 radians, but we are less than 4.71 radian. Okay, so the tricky part might be the coterminals, but not really. So positive coterminal. What does that mean? In radians, I'm going to have to add 2 pi, or 6.28, right, approximately, to this 4.2. So when I do that, it's going to be 4.2 plus 6.28. That's going to be 10.48, I'm sorry, radians. A negative coterminal is going to be this direction, clockwise. And if all the way around is 6.28, I'm going to subtract 4.2, and I'm going to get negative 2.08 radians. Well, what's an expression for all? Okay, for all of them, it's going to be 4.2 plus 2 pi n and an element of the integer set. Okay, and if I was going to do a negative one, I would just be rotating the other direction, remembering the decimals for my quadrant pi over 2's and all of that, okay? Now, one other thing to discuss before I end is how do we convert from degrees to radians? because that's good to know. Okay, so to convert from degrees to radians. Now I want to refresh our memory back in this part of my my notes here. There are many different ratios that we could use as a conversion factor. We could say 90 is to pi over 2, or 180 is to pi, or we could say 108 or 270 is to 3 pi over 2, or we could say 2 pi is to 360. But my experience is that teenagers are allergic to fractions, maybe not all, but most. So we have a choice between 180 is to pi or 2 pi is to 360, and this one's already reduced. So let's use our conversion factor of 180 is to pi. Okay, so now if we are going from degrees to radians, you always put your radian measure where you're headed on top of your fraction. So it's going to be, let's say 30 degrees, and I want to convert that to radians. So I need to cancel out the degrees. So I'm going to say pi is to 180 degrees, because then the degrees cancel, and then I'm left with radians, okay? So then I do my multiplication, and 30 goes into 186 times. So this turns out to be pi over 6, and this is now in radians, okay? All right, let's do another one. Let's do 240 degrees times pi over 180. And again, here we go. The degrees are going to cancel. And I'm going to reduce because it looks like 60 goes into both. So 60 goes into 24 4 times. And 60 goes into 183 times. So this would be 4 pi over 3 radians. So now we're in radians, so we don't have a degree mark. Okay, so what is the factor? The conversion factor here. I can't spell factor. You can spell conversion, but not factor. Here we go. Factor is going to be pi times, or pi over 180 degrees. And I want you to remember that if we're going from degrees to radians, the radians has to be on top because that's where we're headed. And we want to cancel out the degrees. Okay, so what if we are converting from radians to degrees? Okay. All right, well, let's try an easy one. Let's try 2 pi over 3. And I'm going to use a conversion factor that's the flip of this, because now I want to have the radians cancel, right? So I'm going to multiply by 180 degrees over pi because I need the radian measure to cancel. So I'm going to take this and say 180 degrees over pi. All right. And so I can cancel the pi's, and I'm left with, well, 3 goes into 180 60 times. So this will be 120 degrees. All right. So I said that not all radian measures have pi's in them. So let's say I wanted to convert the 4.2 radians that I had on this page that I just did right here. I wanted to convert this to degrees. So let's take the 4.2 radians and multiply it by 180 over pi. And I'm going to use my calculator for that. Okay, so 180 times 4.2 equals 756 over pi. And I could approximate that divided by second pi. And I get 240.64 degrees, roughly, okay? So again, when we're converting from radians to degrees, we put the degree factor in the numerator because that's where we're headed. We're headed to degrees. All right? Well, that's all I have for doing the Smarties lab and an introduction to radian measure. So you guys have a most excellent rest of your day. Thanks.